you all for coming. This is, it's a Saturday. It's the first nice day in, living memory. So I really, I'm grateful that you would come out, on your day off. And you'll get what you pay for. But I hope that it's worthwhile. So indeed, I'm going to, I'm in the astronomy department, as Naomi said, and I also have some affiliation with physics. They sometimes let me in here, and we in astronomy certainly are interested in the physics on the scales of the very large, but I hope to give you an idea of how, and Naomi was alluding to this, that the very large and the very small are intimately related, and that connection is likely to only grow over time as we try to understand these problems that I'll be talking about today. And those problems are the dark side of the universe. So the universe indeed has a dark side, and we'll see it's rather substantial. And so my sort of Hollywood titles are shadow matter and anti-gravity. And by the end of the talk, I hope to give you some sense of what I really mean by those sort of Hollywood titles. And and by the way, again, I really appreciate you coming out. I can't say enough. Believe me, if I were not here, I would be dozing away now. So I'm just really grateful that you guys got up early. And my impression is that there are a couple of people that came all the way from Chicagoland, which means you got up even earlier than everybody else and took a long drive, and I'm very grateful for that. So I hope there's at least some entertainment value here. So if you're still a little woozy, it's been a long, you just got up, your head's a little fuzzy, let me just give you a basic sense of what I'm going to say. I'll give you my conclusions now, and you can decide what you think. If it sounds interesting, you can stay. If not, believe me, it's a nice day. I won't be offended. There's still coffee and donuts. So I'll try to give you some sense of this dark side of the universe. But before I tell you about the dark side, I'm an optimist. I first want to look on the bright side. And before I present a bunch of problems, I want to give you an idea that we really do have some understanding. In fact, an impressively good understanding of how the universe works. And so we'll talk about the bright side and the expanding universe that we live in, and the evidence we have that goes behind this picture we have of the Big Bang, and why we are very confident that we live in a universe that went through a Big Bang. And once I give you an idea of what we're optimistic about, what we know, then I can tell you about the remaining puzzles that are job security for physicists and astronomers, because these are deep puzzles that are going to be very hard to understand. So first I'll talk about this shadow matter, shadows of creation, namely dark matter. So we'll see that most of the matter of the universe is in some crazy form, dark matter, and I'll explain why we believe this and how we hope to figure out what this crazy stuff is. But then you notice here the colors are getting darker because things are getting even worse. And then dark matter is crazy enough, but we at least have some ideas about what dark matter might be, and we have some good ideas about how we might find it. But stuff that's even crazier is this stuff, anti-gravity, I called it. Really, the name is given as dark energy. I'll explain why we call it that, and why it leads to a universe that is accelerating, and why that's bizarre, and how this is a complete surprise. And this is really the most pressing question in possibly in all of science today. What is going on with this crazy dark energy? And I hope to at least give you a flavor of how this stuff all plays together. So we'll go from bright to dark as we go through the talk. But before I present all these mysteries, I want to give you an idea that we do understand something, so you'll appreciate what it means that there are major things we don't understand. So first, let's look on the bright side. And let me sort of set the stage and get you in the mood. So what we're doing here is cosmology, and this is science on the grandest of scales. So we're looking at the truly big picture, taking the universe itself as our object of study. And so to give you this sort of overview, cosmology, it's a very modest subject. We just want to understand the structure, origin, and evolution of the universe. So once we're done, we can go home. So just to give you a sense, so again, we're looking at the big picture here. So we live around a beautiful star, the sun, and the sun is one of many stars in a grouping called the Milky Way galaxy. And on you that live not in Chicago, on a dark night, you can sometimes see the band of the Milky Way in the sky. So our sun is but one of many billions of stars organized into a galaxy. And typically a galaxy might have 100 billion stars. These are a couple of galaxies similar to our own. This is our sort of next door neighbor, sort of sister galaxy called Andromeda. So we live in the middle of a structure like this, so I can't show you a picture of the galaxy we live in because we live inside of it. We can't step back to take the picture. But if we did, we'd have a picture much like this, and our sun would be somewhere around here. But what you're seeing here is an enormous number of stars. This is something like 100 billion stars. And here's another galaxy where you're again seeing hundreds of billions of stars there. So this smear of light is due to innumerable stars that the telescope can't pick out one from another, and they all smear together to make this glow that you see. Okay, so stars are organized into galaxies. And from the point of view of cosmology, we don't even start thinking about objects in the universe until we start thinking about galaxies. The galaxies are really the building blocks of the universe. Actually, in sort of a similar way to atoms being the building blocks of matter, the galaxies are the building blocks of the universe. And they smoothly fill the universe. There are galaxies strewn evenly, more or less evenly, in all directions. In every direction you can go, there are just more and more galaxies, and all spread more or less evenly throughout the universe. So that's the basic structure that we have, and then we want to understand how are these galaxies behaving? How are they moving in particular? And to figure that out, it's not a new result. That goes back to Edwin Hubble. You know, you've heard of Hubble the telescope. This is Hubble the man. He came before the Hubble telescope. I'm proud to report to you that he grew up and was educated in the great state of Illinois. So he grew up in Wheaton. Wheaton fans out there. And was educated at the University of Chicago. And he was the great observer of galaxies. This is all back at the beginning of the 20th century. And it was in the 20s when he did some of his greatest work. And he was the great observer of galaxies. So not just those two I showed, but he systematically studied galaxies. And he wanted to not just take pretty pictures of them, but understand how they're really behaving. He wanted to apply some physics to what's going on with the galaxies, which is a brilliant move. And so what he did for the galaxies that he saw, not just the ones I showed you, but an enormous number, he would measure not just what they look like, but measure their distance and their speed. So they're any given galaxy some distance from us, and in general it's moving. And so he measured both the distance and speed to get a sense of how are the galaxies behaving. Not just what are they doing now, but how are they behaving, and given that they're moving, how might they behave in the future, how might they behave in the past. So there he is in the middle of this effort. Now it seems to be the lights are on when he's observing. That's probably not a good idea. But he was truly a great astronomer, and what he found was revolutionary. So, okay. So to get you in the mood, let's have a flashback. It's 1928. Hubble's great result came out in 1929, so it's a year before. It's 1928. Hubble was busy doing this great work, measuring the velocities and distances of many, many galaxies, an enormous effort. And the question is, what is he going to find? I'll reduce it for you to a multiple choice question, since it's Saturday, we're all waking up. So I'll just make it simple. So so these are just three logically possible results, which include the correct result. So is he going to find more galaxies are coming towards us than moving away? So he's looking at how the galaxies are moving. Or is he going to find more are coming towards us than are moving away? That is certainly logically possible. He could find more galaxies are moving away than are approaching. That's also possible. Or he could find about equal numbers of each. Now, some of you might already know the result, but I'm not actually so much interested in that. I'm just interested in you laying your bets before you see the result. It makes it more fun. So if I could just get a show of hands. So more galaxies approaching than receding. More galaxies receding than approaching. I got a lot of votes for that. About equal numbers? Okay. And some of you may already know what the result is, but now let's go forward to 1929, and here's the result. So here it is. It's 1929, and what Hubble found is that galaxies move away from us. And when I say move away from galaxies move away from us, I don't mean maybe 51% move away from us and 49 come towards us. So, just a little bit more move away. I mean, all of them move away from us. All. By now, we have measured millions of galaxy speeds, velocities really, and they all are moving away from us. Millions of them all moving away. So this is not a small trend. This is knocks you over the head. It's such a strong trend. But it's even more than that. What he found is the farther away a galaxy is, not only are they moving away, but the farther away they are now, the faster they're moving. And in fact, you can write this in a nice little equation, which Hubble did. And he said velocity is proportional to distance, or if you like, velocity is a constant times the distance. That's such an important thing. It gets a name, and that's called Hubble's law. And to give you a sense, if the equation doesn't do it for you, let's draw a picture. So that's sort of an artist's conception, but an accurate one, of how galaxies move. So the idea is this dot is you are here, so that's you. That's us on our galaxy. It's a whole galaxy. So that's the Milky Way galaxy. And then I've drawn some other galaxies lying around near us. And like I said, they smoothly fill space, so they're sort of randomly filling up space there. And on each galaxy, I've drawn a little arrow. And the arrow is giving you a sense of the direction and magnitude of the velocity. That is how fast and where the galaxy is moving. And so what you see is that as you get further away, the faster they're moving. And it makes this sort of very kind of beautiful pattern that you see. That is the pattern that Hubble discovered. That is how the galaxies move away from us. And if I had more space here, I'd show yet more galaxies, and they'd be moving even faster. That is the pattern that he shows, that he found in 1929. So that's a rather remarkable thing that clearly is trying to tell us something. And so this screams out for an interpretation. Something this regular screams out for an interpretation, and there are at least two logical interpretations. So care to guess? Don't be shy. Up and back. There absolutely a logical possibility is that the universe is expanding, and we'll absolutely talk about that. But there's another logical possibility too. So thank you very much. I want to make sure we at least cover one other logical possibility. I'm not saying whether it's right or wrong. We just want to lay out what the possibilities are, and then we'll think about them. That's how it works. Please. Oh, yeah. So you could say that space is being created between the galaxies, which is sort of, that's a similar idea to the idea that the universe is expanding, that sort of there's extra space being created. That's very good. So those are similar ideas. There's a completely different idea. Sorry, way in back? Oh, yeah, and I haven't gotten into the details of that. That's right. Occasionally people have tried to suggest that, there's, at the level we're talking about, I haven't explained enough to give justice to the question. The question is whether we're correctly measuring the velocities. And there are lots of ways to check that, and by now we're very confident that we're measuring the velocities correctly. So this really is the pattern. We're stuck with this pattern. One possibility is this expansion idea. There's one other logical possibility I want to at least get out there, because it's important to give it justice and talk about it. Because you've hit upon the popular answer, but there's another. Notice that all these arrows point back to us, and we seem to occupy a rather interesting position. Thank you. Somebody finally said it. It looks like we are at the center of the universe, because after all, here we are. We're not moving at all, and everybody else seems to be doing a lot of moving. It looks like we are at the center of the universe. That is an absolutely logical possibility as well. So I would describe that as somewhat as the egoist view. There's Monty. It's always about Monty. So you could absolutely say that we are at the center of the universe. And that is absolutely a logical possibility. But it's not, it's not a very popular one. And perhaps suggested by nobody who's in a big hurry to say that. And it's not just because it's unpopular. Although it's a logical possibility, it's hard to see what would make us the center of the universe. Because if, after all, there was a big explosion or something that led us to be at this center, you normally, where there's an explosion, you normally can tell that there's been an explosion, and what's left at the center is pretty remarkable. It's the cinder left over from some nasty explosion, and we look the same as everybody else around us. There's no evidence that we're at the center of the universe, and there's another completely different way of looking at this. Oh yeah, so that's not good. There's another completely different way of looking at that, and that of course comes from Einstein himself. And he said, look, another completely different way of looking at this is the universe itself is expanding exactly as you guys said, and hit on it immediately. And actually, there's no center at all. So that it's as if you can imagine this little square, this little chunk of the universe is made of like a rubber sheet, and we had strong muscular people on all the corners pulling very hard, and the sheet is stretching out over time. That space itself is expanding. And that also leads to this pattern that you see here. And so, but way back in 1929, so Einstein had actually already thought of this idea before 1929, but thought, oh my, he solved his equations for the universe and saw that it would lead to a universe that was expanding. And even Einstein thought, that's crazy. And so he actually fudged his equations, added an extra piece that he had no other reason to add, except to fix up his equations to make the universe sit still. And then, in 1929, Hubble comes along and says, no, I actually see that the universe is expanding. And then Einstein later allegedly said this was his greatest blunder, that he invented this new fudge factor called the Cosmological Constant. He invented this fudge factor to prevent the universe from expanding, when if he just trusted himself, he could have predicted the expansion of the universe. So that's where we are. It's 1929 now, and so the easy way to remember that is stock market crashing, universe expanding. Okay. Woohoo! Yeah. So good. All right. So again, we're trying to apply physics to the universe, and the first major thing to appreciate is we see that the universe is expanding. So if the universe is expanding, then we have to ask, how does the universe behave? If it's expanding now, what was it like in the past, and what will it be like in the future? So let's start and think about the past. The universe is expanding now, so imagine, run the movie backwards in your head, what is it like in the past? Well, if it's expanding, all the galaxies are moving apart from each other. But that means if I run the movie backwards and think about the past, the galaxies are closer together. Fair enough. And so that means the universe is denser. Matter is more concentrated because all the material is closer to all the other material. Fair enough? All right. Well, if you take this idea seriously and just keep running the movie backwards, there has to be a time when the universe was enormously dense. Not just a little denser than today, but if you run the movie back far enough, the universe should have been enormously dense. So dense that now the matter isn't spread out into isolated galaxies, but all in contact with itself. And then there would be flows of energy and heat from bits of matter in one place, bits of matter in the other place. It would come to some sort of equilibrium. The universe would have a temperature. So if you just take this idea of an expanding universe seriously, eventually, in the past, it should have been compressed and rather hot. Great. And so at early times, the universe should have been compressed and heated up. And that means now run the movie forward again. Then from a hot, dense, early state, the universe would have expanded. And as it expands, it should have cooled. Expanding gases like to cool. And so the expanding universe today should be cooling, but the flip side of that is the early universe should have been dense and very hot. Actually, if you've ever pumped up a bicycle, it's the same thing. You pump up the air, and by compressing it, you make it hot. The same thing happens with the universe, and then the universe expands and cools off. So we are seeing now the expanded, cooled version of what was once a very dense and hot early universe. Okay? And this very hot and dense early state has a name. Actually, it took a while to come up with the name, and it's not the best name in the world, but it's the name that we use to describe a universe that begins in a hot early state and leads to what we see today, and that is called the Big Bang. So, all right. So, in the past, the universe had to be very hot and dense, and then expanded. That hot and dense early state is the Big Bang. Okay. So I've given you at least some flavor of how we try to think about this, and in fact, many aspects of the Big Bang are understood and understood rather precisely, not just in general terms, but in rather precisely, where we can make very detailed predictions, actual very detailed calculations where we can predict not just general behaviors, but we can predict what exact results of measurements ought to be, and we can compare them with measurements, and they really agree. So it would be a talk by itself for me to really give justice to all the things we do understand about the Big Bang. But if I gave you that talk, which I would love to give you, then we wouldn't have time to talk about the things we don't understand. So I'm now going to, in a very rapid sort of breezy manner, summarize for you an enormous amount of work, an enormous amount of success in the Big Bang theory. And the main reason I'm doing this is to try to give you some confidence there's something we understand. As I said, any one of these things really deserves its own Saturday morning talk, but time is short. So I'm just going to give you sort of the t-shirt version of each. If you had to buy a t-shirt describing the successes of the Big Bang, each one of these would be a t-shirt. So here we go. So first, I told you the universe is expanding. Well, by now we have an extraordinarily good idea of how the universe expands. So we know that there was a bang, and we know it was big because the universe is expanding quite a lot now. And as I told you, all known galaxies, which by now is millions, it's not a handful, it is millions, are found to be moving away from us. So this is not just some approximate trend. It is an absolute iron law that galaxies move away from us. Hubble's law has been very strongly verified. And we know the present age of the universe, which is 14 billion years old. So we understand the behavior we understand the universe well enough that we can even work out its age, and we have a good understanding of what the universe is doing now. But that's not all. So that's one talk by itself, which I'm breezing over to just quote the result. So another thing is, I told you the universe had to be very hot and dense. Well, if it was really hot and dense, at some point the whole thing should have been so hot that it was ionized. It was basically the same physical state as a flame of a candle. Not the same gases, actually hydrogen and helium rather than air, but that's all right. And so the universe was once an enormous cosmic fireball. And this fireball has actually been detected. It's not a fireball anymore. It's cooled a lot. Now we see the glow not as something you can see with your eyes, but in microwaves. But that's all right. It's the same glow. And this fireball has been detected and understood to exquisitely high precision. For the experts in the room, this is known as the cosmic microwave background, and we have an extraordinarily exquisite understanding of that. And actually, some people here at the University of Illinois have been some of the people driving the research in that field. And so by looking at the remains, the afterglow of this cosmic fireball, that really tells us the universe was once enormously hot. So not only was the bang big, but the big had a bang. So in fact, we've measured the temperature of the universe at various times, and we can actually show that over time the universe really has cooled down. So it's not just a good idea. That's what we actually really measure the universe to do. And in detecting this fireball is telling us about the universe when it was 400,000 years old, which is a long time, but it's very small compared to that. So that's already telling us that we understand the universe more than 99% of the way back to the Big Bang. But we're still not done. Because one other talk, which I could give you, and I would dearly love to give you this one because I do this, so I had to hold back to not say more about this. So we understand the universe is expanding today. If we extrapolate back to 400,000 years, the universe would have been on fire, basically. If you extrapolate back even further to even higher temperatures, higher densities, there comes a time when the universe was a nuclear reactor. The entire universe was a nuclear reactor, and the very lightest elements were forged in nuclear reactions in the early universe, in the first few minutes. And this is a subject dear to my heart. I work on this. And so we can actually predict how much of the very lightest elements were produced in the universe, where they ultimately come from. So if you've taken any chemistry classes, you know the lightest elements are hydrogen, helium, and lithium. And in chemistry class, you study how you combine them with other things and make molecules, and that's very interesting. But you can ask, where did these come from in the first place? And in the case of these elements, hydrogen and helium and lithium, where they come from is the earliest moments of the universe. So, for example, the lithium in your extended life batteries or psychoactive medication, that comes from the earliest moments of the universe. And by measuring how much lithium, for example, is out there and comparing with observations, we can see how well this Big Bang picture is working, and it works incredibly well. And in fact, by our understanding of how much of the lightest elements the universe produces, the fact that that understanding works so well tells us we understand the Big Bang back to a time of 1 second. It's a rather remarkable thing. I mean, the thing I hope to impress you with is it's amazing that we can know any of these things, and the fact that we know all of these things so well is just a fantastic triumph of science. This did not have to go so well. And so the message is that the Big Bang is looking really good. It's just fantastic that we could know any of these, much less all of these things. And to know them so well is just a fantastic thing.
Excellent.
So you can only be happy about that. All right. So I've given you some sense of the bright side. I've tried to give you an idea in a very sort of breezy, quick way of why we believe in the Big Bang and some of the successes of the Big Bang. Now wouldn't be a bad time for some questions just about the basic Big Bang, because I'm about to tell you what we don't understand. I want to be sure we're clear about what we do understand first. So any questions before we go on? Please. Oh, yeah, so right. The question is, so how does this connect with life appearing on Earth? You know, when in this expanding and cooling does life appear on Earth? And absolutely right that it's critical that the universe had to cool down for this to happen, because when nuclear reactions were going on, the whole universe was a nuclear reactor. That's no place to form any life. And so you've got to wait a long time for the universe to cool down, for stars to form and planets to form, and then life can form on at least one planet, namely this one. And we certainly hope, and this is a whole different subject in astronomy, by the way, of finding planets around other stars and seeing if life is formed elsewhere in other stars. But you're completely right. You have to wait for the universe to cool down, and it's only after millions of years that the first stars are able to turn on and make planets, and there's any hope of making life in the universe. So life is an important player in this, obviously, but much later than the very early times I was just talking about. Yeah. Oh, thank you. That's a very good question. It deserves a longer answer than I probably will give it. So, if the universe is expanding, and it is, we see all the galaxies moving apart from each other. Can we even measure expansion within a galaxy? I told you stars are actually in galaxies. Can you watch a galaxy itself expand? Or for that matter, if I push that idea even further, can you see expansion in this room? Am I moving away from you and you moving away from the person sitting next to you? And the long story short is, if the universe were literally perfectly smooth with an even amount of stuff everywhere, then every point would be expanding from every other point. In fact, I don't know of a less technical way of saying this. In a system that's got extra stuff, so galaxies are lumped. One galaxy gathers up material around it and is lumpier than the average amount of universe, and a gravitationally bound system doesn't expand. So galaxies themselves don't expand. That's what I'm trying to get to. So this room is not expanding. Galaxies themselves don't expand. It's only on the largest of scales where the many galaxies are strewn out that they all expand from each other. The galaxies are really the building blocks. They themselves don't expand. That's the bottom line. That will actually become important for a video I'm going to show you in a little bit. So yeah.
So after the Big Bang, at some juncture, were all the galaxies sort of formed at the same time?
That's a really good question. Actually, that is the checks in the mail. That's a very interesting question, and that's actually one of the most interesting questions that people are working on now. When did galaxies form? Did they all form at the same time? And first of all, the answer is I think at this point it's already clear. The galaxies certainly did not all form at the same time, and they aren't born just all at once. Small pieces are born, and then gravity gathers smaller pieces together to make bigger pieces. And so galaxies are sort of formed piecemeal, and there's a lot of small pieces merging together to form big pieces. But the details of that are extremely interesting and still being worked out, and are somewhat related to the things I'm about to talk about. Yeah. Oh yeah, so where did all this matter come from in the first place? And that also is an extremely good question, and that is ultimately related to the things I'm going to talk about as well. So the short answer is we don't know, and in some sense we just said, well, what we've done so far, these great successes of the Big Bang come from saying, look, we see there's matter in the universe now. If I just run the movie backwards, knowing the physics of how matter behaves and gravity behaves, then I have this great success in describing earlier moments in the universe. But at some point you have to ask, where did the matter come from in the first place? And that is a very profound question, and we have some ideas about that, but we certainly do not know the answer to that. But it's probably tied up with the things I'm about to talk about, so I'll leave it at that. Was there another? Excuse me? Oh, yeah, so was it all energy before it was matter? That's closely related to that question, and the answer is that was it all energy, not in a simple-minded way, but it's closely related. But the early history of the universe, it was very, very hot. There was an enormous amount of energy around, and Einstein taught us that matter and energy are closely related. So although there was matter around, it had so much energy, it behaved a lot like energy. And we'll have a little bit more to say about that in a little bit. And, so that's the next thing I'm about to get to. I've given you some hint about the matter we know about. I'm about to tell you about a lot more stuff that's even stranger than what I've told you about. And one last question. Oh, yeah. So, yeah. So that's the thing. The universe doesn't have a center. So the universe is filled with matter evenly in all directions. There's no edge to the universe. Every place you go, you keep seeing more galaxies everywhere. So at earlier times, the galaxies were closer together. But that's why the term Big Bang is kind of bad, because you imagine some kind of cosmic egg exploding, and that's not how it works. It's that all the space between all the galaxies is increasing, but it's not the case that there's some edge to the universe and it's like a bomb blowing up. It's not like that. So at earlier times, every particle is closer to every other particle, but it's not that there's one isolated region everything came from. So the Big Bang happened everywhere. So, all right, well, one we probably should go after. Oh, well, because of the Big Bang, yeah, so the question, if you were far away from the Big Bang, what would it look like? The point is, since the Big Bang happens everywhere, that right here is where the Big Bang happened, where you're sitting is where the Big Bang happened, the next galaxy over, the Big Bang happened everywhere. So, but the point you're making is an interesting point we're going to get to in a second. It's to do with how a telescope is a time machine. So I'm going to get to that point, but I don't want to keep you all day, so we probably should move on. But I appreciate your questions. I don't mean to foreshorten them, but life is short. We should move on. You need to, get your coffee and cookies. So okay, I've tried to give you some sense of the bright side, what we understand, and it's amazing what we understand. But now the dark side starts to loom. So first, I'll tell you about some of these shadows, otherwise known as dark matter. Okay. So a lot of you probably know this, but again, it's Saturday morning. You're probably still waking up. Let me just remind you a little bit about gravity. It's very important for the rest of the talk that we have a very clear understanding of how we think gravity normally should work. And of course, we have Sir Isaac Newton to thank for this, because a long time ago, he taught us about how gravity works. And he said, look, gravity is all about mass. Any two objects with mass exert a force on each other, and we call that force gravity. Okay, and Newton said more than that. Newton explained how gravity depends on the mass of the objects and how they're arranged. In particular, he said, look, the gravity is stronger the more mass you have in the two objects. So for example, if I have a massive object here, maybe that's a star and maybe that's a planet, but it doesn't really matter. If I have a mass here and a mass there, separated by some distance, there's a certain amount of force, a certain amount of gravity. Well, what if I replace this guy with a more massive guy? That just means you get more force. More mass, more force. And it's the difference between carrying a paperclip up the stairs and having to haul a piano up the stairs. Same Earth doing the gravitating, but paperclip and piano, obviously a pretty different experience because you have to exert a lot more force for the more massive guy. You know this already. Okay. Something that maybe is a little bit less obvious if living a life on the surface of the Earth is that the force of gravity reaches out over space, so it doesn't just act on houses and people, but it reaches out throughout space, and the force is stronger for objects that are closer together and weaker as objects get further apart. And so, so here's the artist's conception of that. So if I've got a guy here and another guy there, and they're close together, then there's a strong gravity force. And then if I pull the second guy further away, the force goes down. That's a key point. And it's very relevant to life in the universe, that as you move away, the gravity force falls off. And for those technically inclined, and some of you may have seen this, that gravity then is actually proportional to the, you can write down an equation, it's the force of gravity is proportional to the product of the masses, the inverse of the distance squared, and then there's just a little proportionality constant that makes the math come out right. Okay, so, but if the equation doesn't do it for you, just remember these pictures and that gives you what you need to know. More mass, more gravity, further away, less gravity. Okay, so just as a warm-up problem, let's apply this to the solar system. So we've got the sun, which is a body exerting gravity. Planets move around feeling that force. So, so it's not a trick question, but I just want to get you in the mood. So, so according to these rules, which planet should move the fastest? The one that's the closest, otherwise known as Mercury. So you would expect Mercury to move the fastest. And which one should be moving the slowest? Neptune or Pluto, because then we got to have the whole discussion of what a planet. The one that's the furthest away. Let's just leave it at that. Okay. Okay. So that's all good. And then just for laughs, let's now go to a more advanced problem. Now this applies to this not to a solar system, but to a whole galaxy of stars. So here we have a bazillion stars. So that's a picture of a bazillion stars. And they all are in orbit around the center. I don't think I explained that before, but that's actually true. So all the stars are swirling around in an orbit around the central point of the galaxy. And each star feels the gravity of all the other stuff in the galaxy. Okay? Because every object attracts every other object. So every star in this galaxy that you're seeing here, every star feels the gravity of everything else in the galaxy. Okay, so, so that being the case, which star should orbit the fastest? So you would think the closest to the center, something like that. And which should orbit the slowest? That's actually an easier question to answer. The ones furthest away. Yeah, it's sort of like the solar system problem. Okay, so that's certainly what you would predict based on this little discussion here. Let's see how this holds up against real data. I mean, I'm going to represent the data in an artistic way, but it's a fair representation of the data. So first, the solar system. So here's an artist's conception of the solar system, and let me show you how the velocity patterns work. And that's how the velocity patterns work. So, so as you go out, the velocities drop off like this. And so the more distance you have, the less gravity, the slower motion. So it's exactly what you guys said. So what you would expect based on Newton's gravity works very well. By the way, let me just maybe make this remark as well to look at the problem in a slightly different way. Imagine this guy, let's say that's Neptune. It's nice and blue. It's probably Neptune there. Imagine that if this guy were moving a lot faster than this speed, so if suddenly I gave it a boost and it moved a lot faster than this speed, what would it do? It would escape. It would actually just completely leave the system. If you've heard of something called the escape velocity, if I gave this planet any more speed, it would just completely leave the system and the solar system would start to fall apart. At least that planet would move away. Okay. Great. So you've done very well with the solar system. You're ready for the big time. So now let's look at what happens with the galaxies. Now I'm going to show you what the data tell us. You go and actually make measurements. This is what you find. And so again, a galaxy like this, all the stars are swirling around the center point, and you can actually measure their speeds. And I've drawn little arrows, which are a fair representation of how the speeds work. And what happens is towards the very center, things don't move very fast. Because there's a lot of mass outside, but not so much mass inside, so they don't move very fast. But then the speeds go up, and they come to a peak, and then they just keep going, and they don't change. And that's what you find. So the speeds go up, they come to a peak, and then that peak doesn't go down. It just goes up. And no matter how far I go as far as I can measure, as far as I can go from the center of the galaxy, even when I'm way far away from the center of the galaxy, all the stars are far away inside, the stuff still moves at the same speed. That's what you find. That's the data. That's the real world. So if you were following this discussion, this should puzzle you a bit. Because another way of looking at this is, look, if most of the matter were here, then it should be like the solar system. The further away you go, the more the speed should drop. But that's not what happens. The speeds keep going. Another way of looking at this is, remember, like with Pluto, I said, what if Pluto had too much speed? It would just leave, but these guys aren't leaving. So we see at a large distance, we don't see the speeds decreasing. But that means the gravity from where you see all the stars should be, if I know how much, that there are stars there, I know how much gravity they have, we understand that. The gravity from these guys should be too weak to keep these guys from flying apart. These guys really should be fast enough to completely leave the system. These guys have the escape velocity. They should just leave. This whole system should fall apart if it has speeds like this. In fact, it should have already fallen apart to even be in this situation. So why doesn't this galaxy fall apart? That's the question. That is a big surprise. So somehow, it looks like the center can't hold. It looks like galaxies ought to fall apart. Because it's not just this one galaxy that has the pattern I showed. They all have this pattern. And so all galaxies show this bizarre trend, including our own Milky Way. It's hard to measure for our own Milky Way because we live inside of it. But it also has the same pattern. So no matter how far you go away, the speeds don't drop off, which is what should happen if gravity works the way you normally expect. And the sources of gravity are all clumped in the middle. And so what could this possibly mean? And actually, again, there are two logical possibilities. Maybe these are maybe not as obvious. And people have thought seriously about both possibilities. So there are two possibilities to explain the behavior I just showed you. So care to take a stab? That's right. So there could be an unaccounted for force. There could be extra forces that are holding these particles in, and so that's exactly right. And so what might create extra force? That's right. So if there were extra force because there's extra gravity from mass that we can't observe, that didn't show up in that picture I just showed you, but is there somehow, if we had invisible mass, then that would give extra gravity and could keep the stars from flying away. That is absolutely a logical possibility. There's another logical possibility. Well, so galaxies have stuff, and so there's always, you can always define a center. It turns out, and there are just more and more stars, and they become particularly dense at the center of a galaxy. As you can see, that's why the stars are particularly, the light is particularly bright because there are a whole bunch of stars clumped at the center. It turns out, actually, that's a whole side issue for the purposes of this talk, but it's really interesting. Actually, galaxies typically have black holes at the center. But the black hole doesn't actually itself have a huge amount of gravity. I mean, it's a very interesting object, but it's not, most of the mass that you can detect is in the stars. It's not in the black hole. The black hole is a tiny fraction compared to the stars. So it's an interesting object, but it's not what's causing this problem. So anyway, so one possibility that we've got unseen mass that's keeping our galaxy from falling apart, there is another logical possibility. The laws of nature that we know them as wrong. That's exactly right. In particular, there's one law I was using to right now, and I found a problem with it, namely gravity. So the law that could be wrong is the law of gravity. It could be we do not understand gravity. That is another logical possibility. So let's go through this. So there are two possibilities, and either one of them is actually pretty interesting. We either have grossly failed to understand gravity, because it's not just some a few percent effect. What I'm saying is the galaxy should be falling apart, but it isn't. That means that either gravity completely fails to work the way that Newton taught us, but not only not the way Newton taught us, it's even worse than that. It's because Newton's gravity got revised by a famous guy you've heard of, and his theory has a lot of success, and that is Mr. Einstein. And so if our theory of gravity is wrong, it's not just Newton that's wrong, it's also Einstein that's wrong. And we have lots of reason to believe that Einstein's theory is right. So in general, I'd say people are pretty hesitant about this, and it's hard to have a theory of gravity different from Einstein's that still works. And so so this is absolutely a possibility, and people do look into it. So I'm not trying to dismiss it, but it's hard to make a lot of progress in this direction. It's hard to do a lot better than Einstein. And so the thing that people spend most of their time thinking about is the other possibility that we have grossly estimated sources of gravity and grossly undercounted the matter in galaxies. And I've given you some flavor of some reason why you might believe this. There's additional reason beyond this. In the time we have, I'll just have to leave it at that. So we are now going to spend our time pursuing this possibility, but I cannot rule out this possibility. I can just give you some reasons we think it's less likely. All right. So we have to have a large unseen mass present in these galaxies, which is holding them together, adding to the gravity of the stars. And that unseen mass, it's known as dark matter. All right. So dark matter, let me tell you where we stand on this dark matter thing. So first of all, I can tell you what we know about dark matter, and the name is what it tells you what we know. We know it has to be dark, which means it can't emit or absorb light, because if it emitted or absorbed light, it wouldn't be dark, and we would know about it already, and we don't. So it has to not emit or absorb light. Fine. And it has to, so that's the dark part. The matter part is really, it has to gravitate. We believe there's dark matter precisely because we need extra sources of gravity. So this stuff has to gravitate, which means it has to have mass, because mass is what causes gravity. So we've tried very hard to find out what this dark matter is. This is not a new problem. We've known about it for some time, and we've tried to figure out what it is, and I have to report to you that we've not found anything yet. So one thing I can do, I can tell you, and we've tried to find it, I can tell you what it isn't. So I will now give you a list of what dark matter is not. It is not live stars, because live stars emit a lot of light. That's what stars do. We would know about them. We would see them in our telescope. So live stars are out. That's maybe not a surprise. But interestingly, dark matter is also not dead stars. And this was actually somewhat a surprise, because when stars end their lives, that's the whole talk in itself, but when they end their lives, they leave behind a burnt-out cinder, which still has a lot of mass. And so these cinders, people thought, would be a great place to put dark matter, because they don't emit a lot of light, but they contain a lot of mass. That's the kind of thing you want for dark matter. But it turns out, long story short, this was a big surprise, but we've actually done the experiment, and this is not dark matter. So these dead stars have various names: white dwarfs, neutron stars, and even black holes. We can tell you dark matter is even not black holes. There's an interesting story about how we know that, but I'll just give you the bottom line. It is not in the form of black holes. They would be great dark matter candidates. We would love it if it's true, but that is not what dark matter is. This is rather disturbing, because this is basically the list of stuff you would think of. If you went through the catalog of an astronomer's view of what the universe should contain, these are the best ideas for dark matter, and those are off the table. Because those are off the table, we got to think of something else, and now things become bizarre. So one option is a crazy particle known as a neutrino, my favorite kind of particle. These neutrinos, and Naomi can tell you a lot more about these things, these are ghostly particles which we know exist. In fact, the sun produces trillions of them that go through your hand every second. In nuclear reactions in the sun, they're produced, and they come straight out of the sun and go through your body. They're these ghostly particles. They barely ever interact with anything. And the beautiful thing about them, we know they exist. We've measured them in the lab, and they have mass, and they don't emit light. So neutrinos are a great idea for dark matter. They're not familiar to everyday people, but they're incredibly good candidates for dark matter. And although it turns out even neutrinos can't be most of the dark matter, we already know that. And so what we think is, like neutrinos, which are unseen particles that until a few decades ago we didn't even know about, and there's tons of them in the universe. And what we suspect is there are even more exotic particles, which Naomi and Kevin Pitts, they can tell you about. They actually are trying to find these in accelerators. There are even more exotic particles that we think exist and might be making up the dark matter, which is a pretty remarkable idea. So we can't make the ordinary stuff can't seem to make the dark matter, so we're driven to look for really bizarre stuff. And so what we think is going on is this crazy dark matter has to be made of bizarre stuff, and a good way to make bizarre stuff is to think about the earliest moments of the universe. Because if you remember what I said, in the Big Bang, the entire universe was once very hot and very dense. And if you think about this for a little bit, that suggests a really beautiful way out of this crazy dark matter problem, just in the very nature of the Big Bang. maybe dark matter comes from exotic particles that are created in very high energy states, high energy collisions of the kind that were present in the very early universe. Not just at 1 second, but even earlier than 1 second, tiny fractions of a second, when the universe would have been an enormously energetic place, and energetic places are where particles can be born, and we know that because we can do that in the lab. Great. Oh, right. Yeah. So the idea is these particles would be from these high temperature, high energy environments, and if we can make interesting stable particles that remain until today, they would be fossils of the Big Bang and make up the dark matter. It would be a beautiful thing if that all worked. And so if we really want to understand, this sort of wacky sounding idea, to really test it and see if it has a chance of working, we need to really understand what happens to matter when you drive it to really high energies, like it should have had in the very early universe. And fortunately, we have the tool to do that. And that tool, well, there are two such tools. One of them is working, and the one that's working is in the great state of Illinois, and that is Fermilab, of course. That's the hometown favorite. And so Fermilab, so outside of Batavia, you can visit it. I recommend that you do. It's a wonderful place. So in Fermilab, so there's this tunnel underground, and there's a series of magnets and a little pipe, and we send very high energy particles around in this pipe. You rev them up here in this little ring, and then they go in here in this racetrack over here. They're revved up to enormous speeds, enormous energies, and then essentially at the speed of light, almost the speed of light, and they go around, one goes around one way, one goes to the other, and then they collide with each other with enormous energies, and you look at the result of those collisions. And the hope is that what we're doing is we're recreating the conditions of the very early universe, and maybe we're hoping that we can make, if there were crazy particles created then that are the dark matter, we hope that we can reproduce those conditions and actually make some dark matter in the laboratory. And so, what I'm trying to tell you is we've now come full circle. There's this beautiful connection between inner space and outer space. So Fermilab, we think of it actually as a microscope probing what's going on at very tiny scales of distance, but it's trying to tell us about the early universe, about the largest things in the universe. So Fermilab is not just a microscope, it's also a telescope, from my point of view, and it's telling us about the universe, not today. It's not a telescope for today. It's a telescope telling us about the universe when it was about 10 to the minus 12 seconds old, and we're hoping that it can recreate the primordial soup, which maybe contain these exotic dark matter particles, sort of like neutrinos. But as soon as you realize this, it's even cooler than that, because if you sort of turn the problem around, you can think of the universe as the poor person's accelerator. So the idea is that, and this is the famous Russian cosmologist Zeldovich said this, that the universe, because it went through an incredibly extreme state of high energies and high densities, the universe went through conditions that we can't even recreate in the laboratory. The universe was once more energetic, particles were more energetic than even we can create in Fermilab or at the LHC. So the universe, for free, has done high energy physics for us, and if we're just very clever and study the properties of the universe, we can maybe learn about what goes on at the very highest of energies. And that's just, to me, that always remains a beautiful idea. That's an idea I never get tired of. All right? So there we go. So that's our thinking about dark matter. So again, I've tried to tell you why we believe in the Big Bang. Then we've got this puzzle that there's all this dark matter out there. And we think that maybe this has something to do with the earliest moments of the universe and elementary particles. And now things will get even worse still, because we're going to hear about anti-gravity and dark energy. Okay. So to get you in the mood for this, all this sort of heavy-duty stuff, let me set the stage. We're now going to go back more than 20 years. The crazy state of the universe was actually predicted not in a scientific publication, but in a wonderful movie called Annie Hall. This is a Woody Allen picture. The astrophysicist, cosmologist Woody Allen came up with this, and it got the Best Picture Award in 1977, which means it beat out Star Wars. Although I love Star Wars, it is a really beautiful movie. And let's see if I can get this to work. Oh, good. So this is a scene. I'm not going to give too much of the movie away. No spoilers. This is right at the beginning of the movie, and this is not like South Park. I mean, you're not going to roll on the floor, but it's very sort of cute. And this is right at the beginning of the movie. You don't really need an introduction because it's right at the beginning. I'll just play it for you.
Out of his mouth, who wanders into a
Whoops.
cafe. Cafeteria with a shopping bag screaming about socialism. Annie and I broke up, and I still can't get my mind around that. You know, I keep sifting the pieces of the relationship through my mind and examining my life and trying to figure out where did the screw-up come, you know? And a year ago we were in love, you know, and I just, and it's funny, I'm not a morose type. I'm not a depressive character. You know, I was a reasonably happy kid, I guess. I was brought up in Brooklyn during World War II.
He's been depressed. All of a sudden, he can't do anything.
Why are you depressed, Alvy?
Tell Dr. Flicker. It's something he read.
Something you read, huh?
The universe is expanding.
The universe is expanding?
Well, the universe is everything, and if it's expanding, someday it will break apart, and that will be the end of everything.
What is that your business? He stopped doing his homework.
What's the point?
What has the universe got to do with it? You're here in Brooklyn. Brooklyn is not expanding.
It won't be expanding for billions of years yet, Alvy. And we've got to try and enjoy ourselves while we're here, huh?
All right. So, like I said, I'm a fan, and one of the things I like about that is that just about everything everybody says is true in its own way. So it's true that the universe is expanding. It's true the universe will be expanding for billions of years. It's true that Brooklyn, as we were saying before, Brooklyn is a part of a galaxy. Brooklyn is not expanding. And we got to enjoy ourselves. The only thing is you do have to still do your homework. So no, not doing your homework. Now, one thing is, when I first saw this, you know, the young Woody Allen seems to think that the universe is going to rip apart. And I just thought that was all very silly. And it turns out, well, we'll see that that's maybe not as funny as we once thought. So, all right. So, okay. So where are we? So as Woody Allen was telling us, the current situation is the galaxies are moving apart from each other. So now let's think about the future, not the past. The galaxies are moving apart from each other. They're expanding. Great. But of course, the galaxies have mass, both visible mass, and actually more than that, because we just discovered galaxies contain dark matter. So they have enormous amounts of mass. Because they have mass, they certainly gravitate. But now you know how gravity works. And so you can predict how should gravity affect the expansion of the universe. So all the galaxies are out there, they're moving apart from each other, but they're also pulling on each other. So do you want a faster expansion in the past, slower in the future, or a slower expansion in the past, faster in the future? So given how gravity is supposed to work, which way do we want to go? Faster in the past, slower in the future? Slower in the past, faster in the future. Okay, so here we go. Well, it's this one. That's for the way gravity is supposed to work is gravity is an attractive force. Things pull on each other. And so the galaxies pull should slow their outward motion. Although they're trying to move away from each other, they're also pulling on each other, and so that should slow the expansion. That's what you would expect. And that's the thing we'd like to learn about. So now we want to get a sense of how does the expansion of the universe change with time? And we can see if we can test this idea of how is it that the galaxies are slowing down over time. And to do that, someone already was alluding to this, we're going to do some cosmic archaeology. We're going to use telescopes as time machines. And now, this is Hubble, not the man, but the telescope, being launched out of the space shuttle there. And so, the beautiful thing is, a telescope is a time machine. And here's how it works. This is not to scale. So here's the Hubble Telescope. The Hubble Telescope, so it's a telescope. You point it out in space, and it takes very beautiful, sensitive pictures of whatever it sees. Well, the universe is filled with galaxies. So here's just a little swatch of it. So this is the field of view of the telescope. So there are more galaxies all around here, but this is what the Hubble actually sees in a given place when you point and click. Because it's basically like a digital camera. It's very much like a digital camera, just much bigger. So you put it in orbit, point it towards some region of the universe, and click, and what you see is you'll see some nearby galaxies and some distant galaxies. It's whatever's there, that's what you'll take a picture of. And if you think about it, the nearby galaxies, because they're nearer, those will look bigger in the picture, and the more distant galaxies will look smaller in the picture. Fair enough? It's the same way like if you were at the football stadium, you take a picture, the heads near you will look big, the heads far away will be little dots. That's the whole picture shows whatever's there. Okay, great. But there's a neat thing. So you'll see both nearby stuff and far away stuff in this picture I'm going to show you. But the stuff that's farther away, let's think about this. The stuff that's farther away, what we're really seeing is the light that was emitted by all of these galaxies. Each one emits its light, and that light makes its trip until it lands on the Hubble Telescope. Well, the farther away a galaxy is, the longer it takes the light to get us. So at a given time, if you take a picture, you're seeing this galaxy, its light hasn't taken very long to get us, but this galaxy, its light took a long time to get us. So the more distant objects, the light took longer to get to us, which means you aren't seeing them as, in fact, for all of them, what this means is you never are seeing the galaxy as it is now. You're seeing as it was sometime in the past. In particular, you're seeing as it was when the light started its trip. You're seeing this galaxy as it was a little while ago, this galaxy as it was a very long time ago. And so the light we see now started long ago. And so I'm going to show you a picture that was taken in this way, where you point the Hubble telescope, expose it for 2 weeks at a time, and then you can see as deep as it is possible to see. That's why it's called the ultra-deep field. And the most distant object you will see will be the universe at 10% of its present age. But the point is, you will see these objects which are telling you about the universe a very long time ago. These objects will tell you about the universe a medium time ago, and these objects are telling you about the universe recently. So in one picture, you will actually have encoded the history of the universe, or 90% of the history of the universe, which is a neat little trick. That's one of the beauties of astronomy. So now that you appreciate what you're going to see, I'll show you the picture, and you'll have some appreciation for why it's beautiful. And that's the picture. That's the Hubble ultra-deep field. And so again, this is pointing the Hubble telescope in one region of the sky and just seeing what you see. So these guys, the pretty-looking objects here, are nearby galaxies that we're seeing from the fairly recent past in the history of the universe. The thing you should respect, these tiny little smudges that don't look like much, they deserve your respect because those are objects that are enormously distant and are sending us signals from what the universe was like possibly 90%, depending on the object, 90% of the way back in its history. So this is a gorgeous picture with its data. This has encoded in it the history of most of the life of the universe if we can just untangle that history. And so that's what astronomers try to do. And in fact, this is one of the ways they try to do it. So we want to decode the history of the expansion of the universe. So if we want to learn about a long time ago, we've got to look far, far away, in galaxies far, far away. But the nice thing is, nature has kindly provided us a way of looking far, far away. There are cosmic beacons, which are known as supernovae, which are really exploding stars. And in fact, I've shown an example here. There are two things in this picture that should catch your eye. There's a big swatch of light here. You've seen this kind of thing before. That's a galaxy of stars. That's 100 billion stars. And then there's this thing. This is one star on the outskirts of the galaxy, sort of the suburbs of the galaxy, and this one star is exploding. So here we have hundreds of billions of stars. That's one star. And this one exploding star is about as bright as all of its neighbors, all the rest of the entire galaxy. So the one exploding star can briefly outshine, and they brighten in predictable pattern. So this star just exploded, and after a few weeks it'll become dim and then you won't see it again. This happened in 1994. If you look there now, you wouldn't see it dim, and the explosion is over. So by looking for these guys, they're very bright. These beacons go off, and by looking at these beacons, we can see them from far away, and we can make very accurate measurements of distance. And so the way we're going to do this, we're going to use a telescope as a time machine, measure these supernova explosions, these beacons, because they're great ways of measuring distances, and use these to find out at any given distance, at any given time, how fast is the universe expanding? And then we're going to see how does the expansion rate change over time? Does the expansion speed up over time, or does it slow down over time? And if you recall, because of the attractive force of gravity, gravity is supposed to make the expansion slow down with time. That's the whole game. And here's the result. So we do this. So we look from here in the Hubble Telescope, we look back in time to all these crazy galaxies with their supernovae. And as we look at these supernova explosions, what we see is that a long time ago, the universe was slowing down, but in the recent past, and by the way, for a cosmologist, recent past means in the past billion years. In the past billion years, the universe has not been slowing down, it has been speeding up. It is not decelerating. Gravity isn't slowing it down. Instead, the universe seems to be accelerating. It is speeding up. The galaxies are not only moving apart, but they're moving apart faster over time. The further away they get from each other, the faster they're moving. So the expansion is speeding up with time, and the universe is accelerating. That is the opposite of this little exercise we went through. It's the opposite of what you would predict. And this was an enormous surprise when people found it. So the universe is accelerating. The expansion is speeding up. But I told you, and you figured out on your own, that ordinary matter and ordinary attractive gravity lead to the opposite result, lead to deceleration. But that's not what we measure. Too bad. We measure acceleration. And so there are two possibilities. By now you're used to this. So one of them is the two logical possibilities. Gravity, as we understand it, predicts deceleration, and we see acceleration. So two things.
Gravity doesn't work as we
Well, once again, maybe we just don't understand gravity, or there's something else that's making this, the gravity is working the way we think, but something else is making the universe make the universe accelerate. So either ideas about gravity are wrong, which makes Einstein unhappy, or most of the universe is not made of ordinary matter, but most of the universe has some strange repulsive effect, and that's why I used anti-gravity in the title. Because if we're going to make things speed up as they get further apart, the only way to do that is not with normal gravity. That's kind of an anti-gravity. And it turns out even dark matter, like normal matter certainly does not anti-gravitate. We're not flying away from the surface of the Earth. But even dark matter doesn't do this. Dark matter is still normal attractive gravity. The only repulsive substance we know about are certain kinds of energy fields, but not even the energy fields you know about, like electricity. That doesn't work either. Or magnetism. That doesn't work either. And so we can dream up energy fields, but they aren't the kind that have ever yet been discovered in the laboratory. So the situation is that if there's some crazy stuff in the universe causing acceleration, that stuff has to be exotic forms of energy. And so really, for lack of a better idea, we just call this stuff dark energy. That's the stuff responsible for the acceleration of the universe. And if that sounds bizarre, it should. And unlike dark matter, I should say, when we came up with dark matter, people already had ideas. Remember I said dark matter is supposed to be these elementary particles, and people had ideas about elementary particles that fit very well with the idea of dark matter. With dark energy, nobody had any good ideas. It was a total shocker. So, I want to make sure you get a sense of the lay of the land. I don't want you to memorize the numbers, but get a sense of how things stand. When I say there's dark matter and dark energy, I want to make it clear there's not a small amount. The ordinary stuff in the universe, and to me, ordinary is anything made of any kind of atom in any form in any phase. That, to me, is ordinary. That is 4% of the universe. That's it. The rest of 96% of the universe is dark. The dark side of the universe is most of the universe, by far. So something like 22% is in the form of dark matter. So most of the matter in the universe isn't ordinary matter, it's dark matter. But most of the stuff in the universe isn't even dark matter. 74%, the vast majority of the universe, is dark energy. So this is not some kind of small little thing that we're confused about. We're confused about it, but not because it's some small detail. It's most of the universe, by far. Who ordered that is the pressing question of the day. We have no idea why this is the case. So we would certainly like to understand this better, because I hope you get the feeling that we don't understand this very well now, because this is just a complete surprise. And so fortunately, experiments are going to come online, telescopes, that are going to help us try to get a better handle on what's going on by at least making better measurements. And the idea is what these new experiments will do, and people here at Illinois are working on both of these things. They're going to scan the sky and look for changes. That's an interesting thing to do anyway. So every night, they will scan the entire sky, and these enormous telescopes will take very sensitive images of the entire sky, night after night after night, just keep sweeping over the sky. And when they do that, these will be digital pictures, so you can download them and everything. And night after night, you can compare one digital picture to the next and see how things change. So you will get a movie of the sky for years on end. And here's the kind of thing you can do. You can look at a galaxy here over time. And so this is not one of these projects. Yeah, this is sort of a warm-up exercise for how this would work. So you look for a galaxy here, and you look at it night after night after night, and some nights you can see better than others, and so things change a little bit. So you look at a galaxy, and every once in a while you'll see that something happens. Now if you just look at this picture, it's going to be hard to tell, but the cute thing is these are digital images. So you can take one image, subtract the image from the beginning, from what you see now, and see what's left over, and that's what you see there. And if you look, what's not so obvious in the raw image, but after you do the subtraction, you can see there's something that comes and becomes bright and then goes away, and that's one of these supernova explosions. And these experiments will discover millions of these things all across the universe. And so it'll discover these supernova explosions, these beacons, and these beacons are great for measuring the acceleration of the universe. And by making very careful measurements of the acceleration, we'll have a better understanding of at least how it behaves, and that will help us rule out, or rule in or rule out, are various desperate explanations of what this dark energy is. So the way to move forward in science when you're confused is to get more data and try to build a better theory to understand the data. These experiments, which are going to happen at Illinois and elsewhere, will do this. Okay. You've been very patient. We've come all the way to the end. So here's where we are. I want to sort of leave you with these thoughts. So the Big Bang as a whole is in great shape. Well, as I told you, it's amazing that we understand the universe 13, 14 billion years old. We understand it down to times of 1 second. That's fantastic, but there's plenty of stuff we don't understand. And so this is a great time to be doing cosmology, because right now is this golden age. Right now we know a lot about how cosmology works, but there are these pressing new questions. We know that there's tons of dark matter and dark energy. We can very accurately make that pie graph I showed you, but we have no idea what dark matter and dark energy is. So there's this enormously pressing question to work out what 96% of the universe is. And the stakes couldn't be higher, because that means the universe is either filled with exotic matter, or we have fundamentally misunderstood gravity. Einstein was wrong, and there's some totally new thing going on with gravity we've never understood. Either one of these is an incredibly fundamental thing, and we're developing new tools to do this, and some of those are happening here at Illinois. And so this is an expansive, as it were, future to be in, and so so you can stay tuned, but you can do more than stay tuned. This isn't actually my last slide. My final slide is, you might, in case this sounds interesting to you, you might ask, how can I join the fun? One way is to study physics, perhaps at Illinois, but I should just point out I'm also in an astronomy department, so studying physics also means you can study astronomy. You can do both. So let me just remind you a little bit of that you can be an astronomy major, and that there are interesting reasons to be an astronomy major. So forgive me, this is a David Letterman reference, but I wrote this before, well, recent events. So from the home office in Urbana, Illinois, top 10 reasons to major in astronomy. It integrates all areas of physics. So astronomy is like a smorgasbord. You get everything. It's not just isolating one little bit of physics. It integrates everything. So, and in fact, we have many double majors who take both physics and astronomy. They fit together enormously well. In fact, astronomy also has connection with the rest of all of science, with geology, chemistry, even biology. At Illinois, if you come and do astronomy, that's great, because central Illinois is very flat, but that means more sky to look at. You develop all kinds of good critical thinking skills, problem-solving skills. You get all of Douglas Adams' inside jokes. So all of his little jokes about, quarks and quasars, you will get them all. 2 words, Hubble Telescope. You saw some of the pictures. It's much better at parties than accounting. So, if you want to impress your date, astronomy, they're close in the alphabet, but astronomy will get you much further. So the pretty pictures that you see, those are homework. Those are data, much better than accounting. And then you can be part of this golden age. We're learning now fundamental things about cosmology, black holes, planets around other stars. Now is a great time to be learning about all of this, and it's just a lot of fun. So on that note, I thank you for coming out on Saturday and for your attention. If anybody needs to go, I won't, please take off, but I'll take questions for.
Why won't the dark matter and dark energy drastically affect your explanation of the Big Bang?
Oh, well, the dark matter and dark energy absolutely do. So the question is, did dark matter and dark energy drastically affect our explanation of the Big Bang? And they absolutely do. And so,
But you said it was well understood.
oh, well, so what I mean by that is that we understand that the universe is expanding. We understand how the universe was once a cosmic fireball, how the universe was once a big nuclear reactor. Those things happen even in the presence of dark matter and dark energy. But in general, what you're saying is right. One of the things that, as we discover more about dark matter and dark energy, what you say is exactly right. You have to have a single understanding, a single theory that includes all of this stuff. So as you understand properties of dark matter and dark energy, you have to make sure that you are correctly including those in understanding the full history of the universe. So that's exactly right. And as far as we understand them now, those are already built into our discussion and actually aren't very important for our discussion of the fireball and of the production of the lightest elements. Oh, yeah. So the long story short is, I actually was doing that all along. I already was using a picture which included all of that when I was doing all of it. There's a longer answer to that, but that's the short answer. So, because I knew, at the beginning of the lecture, I knew where I was going, so I already was including all of that I didn't bother you with it at first. Yeah. Yeah, please. Yeah. So right. So the very observant point was that. Let's see. Yeah. So the very observant point is, in the recent past, the universe has begun accelerating. Like I said, to a cosmologist, recent means 1 billion years ago, because the universe is 14 billion years. So 1 billion years, that's like yesterday. But in the more distant past, we actually see the universe was decelerating, which is the thing we thought it should be doing. So the acceleration is a recent phenomenon. So what it looks like, the dark energy has become more important with time. And in fact, what we think is, although the dark energy represents 75% of what's driving the universe today, it was less important in the past. The other densities were higher in the past. And understanding that trade-off, it helps a lot in trying to figure out what this dark energy is, and that's why we're so keen on measuring very accurately how this transition from acceleration to deceleration works. By measuring that very accurately, that's telling us about the properties of dark energy, and we need all the help we can get because we're so not filled with good ideas about what this could be. So we're hoping that the careful measurements will sort of lead the way in suggesting to us what this stuff could be. Yeah. Thank you. That is a very good question. That's exactly the right way to think, and a lot of people have thought about this. So the question was, I told you that these explosions, these supernova things, are telling us about dark energy. And so that's great, but you say, what if we've made some kind of mistake? What if these supernova explosions aren't reliable witnesses? Then maybe there really isn't a problem at all. And in fact, at the very beginning, when this stuff first came out, that was everybody's attitude. That, okay, you guys have just made some kind of mistake. You people who've pioneered these measurements, you guys just made some kind of mistake. It's great that you found your supernovae. It's really beautiful, but you've made some kind of mistake. And once you fix it, we're going to get a very normal result. And two things. First, people have studied this in great detail, and with trying to find a problem, and no one has been able to find a problem, and it's not for lack of looking. There's fame and fortune to be had in figuring out what this problem would be. No one has been able to find a problem, and believe me, they've tried. But there's actually more going on than even what I've said. There is completely independent evidence for not precisely for dark energy, but what I showed you here. Let's see. Sorry. That's good for you to see anyway. So to give you sort of, there is independent. Here we go. So I said 70% of the universe is dark energy. Well, where this comes from is when you measure these explosions and you see the universe is accelerating, oh my goodness, and you say, okay, how much dark energy do I need to make the universe accelerate? Well, you need 70%. You need an enormous amount. There's a completely independent thing you can do is you can just ask how much stuff is there in the universe total, and how much of that is dark matter and ordinary matter. That's a completely separate question. And you do that, and that also says 75-25. So we have two independent ways of getting that answer. And both things, the second way doesn't guarantee that you have dark energy, but it says that the matter is about 25% and the rest has to be something else. And lo and behold, that's not just a similar idea to dark energy, it even quantitatively gives the same 75%. So that gives us some reason to believe this isn't just a problem with one way of measuring it. But what you say is actually still a big deal. And one of this dark energy survey stuff I talked about, they actually are using more than just the supernova technique. There are several techniques they're using precisely because we worry a lot about whether we're fooling ourselves. Because one of the main things about science is you have to be very careful not to fool yourself, and so we're trying hard not to do that. But I mean, it's a very difficult business. So it still is not impossible that there could just be some fundamental thing going on that we're not understanding, but it has to be a pretty profound thing. There has to be something very interesting and unusual is going on one way or the other. And dark energy is our best bet, but it could be there's some, like, could be with gravity, it could be there's something else that we're just fundamentally misunderstanding. Oh, thank you. Yeah, so that was a very well-informed question. So the question is, I've talked about dark matter and dark energy, but I tried to make sure you're aware of the other possibilities. It could be that we just don't understand gravity. Like I said, we have a lot of evidence that every time we can do a careful test of gravity, which really means Einstein's gravity called general relativity, it works incredibly well, and so that makes us hesitant to think that there's some major problem. But that isn't the same as saying that there couldn't be something going on. And one particular idea for a new kind of gravity is this thing called modified Newtonian dynamics or things like it. And it turns out that it's very hard to make that work. It's easy to come up with a new theory of gravity that explains one aspect of dark matter, maybe to explain how galaxies work. But then if you find a larger system, clumps of galaxies, or the universe as a whole, the thing that works, the modified gravity, the non-Einstein gravity that works for one system fails for another system. And so it's very hard to find, that's what I was trying to allude to. It's very hard to find a new theory of gravity that replaces dark matter. It's very hard to find something that, it tends to only work for one thing and fail for other things. And the way science works is you don't get partial credit, you've got to explain everything. And so to explain all the data, we don't have an alternative theory of gravity that does that very well at the moment. But it still is not that still could actually be the case. It could be we just haven't thought of the right theory. But at least for what we thought up till now, the dark matter seems to work better at the price of being this huge chunk of the universe we don't even know what it is.
Jumping back to dark matter, is dark matter like ubiquitous everywhere in this room?
Oh, absolutely. Yeah. Dark matter, let's see. Well, we don't know exactly what it is. So but certainly if it's the thing that we think it's most likely to be, which I was alluding to, like these crazy elementary particles, then yes, dark matter is in this room. And in fact, if you come to Illinois and take my class, you will calculate, and it's not even that hard to calculate, how much dark matter, and it's these crazy things, these crazy particles that just typically they pass through you. They barely ever interact with anything. And you typically have several hundred in your body. And my students in my class, astronomy majors in my class, calculate that you have something like 500 dark matter particles at any given time. They pass in and out, but at any given moment you have several hundred in your body. If this stuff is even right, there's several hundred in your body, and always were and always will be. Yeah. Different ones, but they come in and out. It should be everywhere. And we take advantage of that in trying to detect these. We actually have experiments underground where we try to, very once in a while, a dark matter will actually bump into ordinary matter, and we actually try to measure this by putting hypersensitive experiments which actually try to detect these things. And so, they're becoming more sophisticated to the point where they ought to start seeing some sort of signal. So that's one of the other ways we have of trying to test this crazy idea that dark matter could be these exotic particles. We have actual experiments that are trying to really rule this in or out.
You mentioned early on in the lecture, the universe has no edge. I'm trying to kind of grapple with the idea of the universe has no edge. Is there a physical analog of anything that's occurring here with that?
Oh, yeah. So this is the business of the universe not having an edge. Yeah, and this always bothers people. And well, so as far as that goes, first I should say, if I did, in some ways it'd be much easier if the Big Bang were from some sort of egg, some sort of confined sphere that then exploded. In some ways it'd be much easier to think about. And I'm always slightly tempted to even just say that and then sort of gloss it over. But it's not the truth. And I owe you guys the truth. I mean, if this were not the University of Illinois, some lesser school, I don't want to name names, but Indiana, they might say something like that. But here, Illinois, we owe you guys the truth. At some level, you can view this as it's an experimental question. What is the extent of the universe? And as far as we know, the universe goes on without end. So we think the universe, as far as we know, is infinitely big. And is that okay or not okay? Well, you can view this as an experimental question. I mean, the closest thing I can think of is like the number line or the the three-dimensional Euclidean space. That's infinitely big, and is that kind of weird? Well, it's kind of weird, but you get used to that a long time ago, and you just come to grips with there's this idea of infinity, and it's a little hard to think about, but you get to where you can deal with it mathematically, and you go on with your life. And so that's sort of how we think about the universe as well. Yeah, that's a very good question. So the question is about, when we measure the universe, we're looking at radiation, which is to say, typically meaning light of all kinds. So I showed you pictures taken with visible light, but we actually can take X-ray pictures of the universe. We can take infrared pictures of the universe. We can take radio pictures of the universe. And in fact, we do. And in fact, astronomers use all known wavelengths. And there's something interesting to see at every wavelength. But the question is there some other radiation we could look for? Well, we look at all light, all electromagnetic radiation. But a very interesting question is, can we look for other kinds of signals, not just light, but other kinds of signals like neutrinos and exotic particles? And that's actually exactly what we're trying to do. So particles like neutrinos, we actually actively, there are ways of measuring those as well. And you can learn about the universe that way. There's a very active effort to do exactly that, to looking at things that aren't light but still carry information about the universe. There are even more exotic things called gravity waves, and we would love to detect those at some point. Those would also have an enormous amount to teach us about the universe. All right. I worn you out? All right. Thank you very much.